And just to get started here, I'll be talking about the fundamentals of accurate mass today. I've tried to bring it back to the basics. So this is, a very beginner level kind of training. This is the kind of information I present when I go on site to help people who maybe have just purchased a high resolution instrument and are just getting familiar with it. Hopefully, I'm able to break it down. This is what I'm trying to do, is just kind of break it down to level to let you understand and give you some basic concepts and some basic terms. This is part 1 of a 3-part series. Part 2 will be on March 9th. And this part 2 will get into a little more in depth about workflows, target analysis, quantitation. And then there'll actually be a part 3 to this as well. And that, as Carl mentioned, will be non-target. So just getting started today, what we're going to look at is first an introduction to mass spectrometry and what is it. I'm going to talk about some of the basics that if you're familiar with mass spectrometry, you've probably heard these terms before. It's always good to kind of go back though and refresh yourself with how some of these things are calculated and why they're important in the first place, why we even care about them. And then at the end, kind of put into the context of a realistic, actual workflow. Okay, so first of all, mass spectrometer. I like to kind of do this because I don't always know where words come from, but the word mass, Isaac Newton first used back in 1700, Latin for loaf, as in a loaf of bread, because I guess something with mass is like a loaf of bread. It's like a lump. So that's kind of interesting. Spectrum is kind of like the word specter, like a ghost. So it's an image or apparition. And then meter is to measure. That's a little more common word. But what we're really doing is we're creating an image, and that's usually a mass spectrum or a chromatogram from data that has been used to say, to measure the mass of a compound, and mostly to distinguish between different compounds of different masses. So really what we're doing, as shown in this example, is we're taking a chemical, ionizing it, and then creating some kind of image that we can then manipulate with data analysis. So in its simplest form, there's what mass spec is. And then I always like to go back to history. So mass spec was around before the 1930s. This was like almost 100 years ago now. But one of its first biggest applications was actually in the Manhattan Project. A lot of big chemical advances, for better or for worse, since this was used to create atomic weapons, actually happened during this time. And they had a preparatory level mass spectrometer used to separate uranium and 238. So in this, they use a magnetic field. It separates out the isotopes, and then you get this early look at a mass spectrum where you see uranium-235 here and uranium-238. Obviously, this is more of an engineering application than an analytical application. But when you look back at these old, histories of mass spectrometer, I find that this stuff is very cool at, the reasons why a lot of these technologies were developed. So I'm going to first talk about a few of the common mass spec, and I said before, we're starting down here at the very basics. So if this is way too much review for you, that's fine. You can multitask, but hopefully this will help some people. So with an ion, the first time I learned about ion trap mass spectrometry is back working with a GCMS, and the engineer that trained me said, think about it like a bucket, and you're filling the bucket with ions. You can think of that like maybe with fish. And then you're slowly emptying the bucket out and emptying the bucket out in a way that you can pick those individual fish out by the size. And the reason he used the bucket analogy of anything here is he was explaining to me the concept of overfilling an ion trap. So ion trap has a certain capacity. You fill it up. You want to fill it up for a certain amount of time, get all your ions, or in this case, your fish in there. If you overfill it, then you have problems. You get space charge effects. You can think of those fish kind of like attacking each other or just spilling out the top. So there are that's probably a drawback to ion trap mass spectrometry. The good benefit is you can obtain very high resolutions and you can be very specific when you do this kind of mass spectrometry. A drawback to ion trap, other than that, is it takes a little more time when you trap because we're having to take time to fill the trap and then time to empty it. The next kind of technology that I think more people are familiar with, if you've done mass spec in the past, probably what you're familiar with is Quadrupole. So even if you've done high resolution mass spec or just standard nominal mass spec, you've probably ran into a Quadrupole. And if you haven't, I like to think of this more as a filter than like a balance or scale. We are measuring mass, but the way we do it is by selectively filtering out different masses of ions using voltages and RF voltages in these almost like a tunnel is what the Quadrupole makes. So you're tuning it, and you're using a very specific set of tuning parameters to let certain ions flow through at a certain condition. So in this way, Quadrupole is great at being very fast and specific. So you can set the conditions of this Quadrupole and here this net to maybe just let that pink fish flow through. And when you do that, you can do it very quickly. You can get very, very good transmission of your ions. That means when you run these Quadrupoles, you can get very good sensitivity just because the transmission is so good. I'd say the drawbacks of Quadrupole mass spectrometry are resolution maxes out, and we'll talk about the definition of resolution here in a few minutes, but you really can't distinguish too much. You can't be as specific as you can with high resolution techniques. You can be really fast, really sensitive, but you don't have high resolution. And so it's difficult to get really good full scan data with the Quadrupole. But the Quadrupole becomes extremely important when we do accurate mass, and I'll talk about why in a bit when we talk about some of the tandem mass spec techniques. And so in a triple quad analysis, I have just a little diagram here. Again, a lot of you probably seen some of this, but just kind of going back to basics here, what we're doing in a Quadrupole, and you can see here, this is a triple Quadrupole. So this is actually 3 together. And this is probably the gold standard for quantitative analysis. So when you have an analyte, a targeted analyte, you want to know how much of that analyte is in a sample. This is the real gold standard of techniques. So what we would do is we have a mixture of lots of different compounds. We set that first Quadrupole to a very specific mass so that only a certain ion goes through. Here the example is 215. So we've let 215 through, everything else goes out into the vacuum. And now what you can do, since we actually have 3 Quadrupoles here, you can get pretty creative. In the second Quadrupole, we pump in a lot of nitrogen or argon, some kind of heavier gas, and we bust that compound into multiple pieces. So this kind of fragmentation is what makes analysis with a Quadrupole much more specific, because you're not only looking at a compound, you're looking at fragments of that compound. And then finally, we use that third Quadrupole to select one specific ion, and then it hits a detector and creates a signal. And if you're familiar with this type, that's great. The pros of this are it's very fast, can be very sensitive, very, very good ion transmission. And that's kind of why it's the real targeted quant tool. The limitations here are, we're selecting for one ion in Q3, even though if we back up here, even though we created lots of fragments, we only see that one. You could run a scan where you see more, but those scans on a Quadrupole are very slow because you pretty much have to cycle through all the masses and then look at the data afterwards. So the limitations of triple Quadrupole there for things like for wanting to know what else is in your sample, or wanting to know more information about your sample, is what leads a lot of people to high-res mass spectrometry. So high-res, high resolution can be achieved with our next type of instrument here. So time of flight mass spectrometry, and if you're not familiar with this, it's very much what it sounds like. It's a race between the fish. So in this case, the little guy wins, so good for the little fish. This has to do with kinetic energy, and the kinetic energy you apply to an ion. A smaller ion will actually have a higher velocity, and that's about as far into physics as I go. But through our time of flight mass spectrometer, the small ions will fly faster. And if you do some kind of curve or turn in the mass spectrometer, we call that, we use a reflectron. So sometimes you'll get one turn, sometimes you'll get 2 or 3 or 4 turns in a time of flight mass spec. And when we do this, the bigger ions kind of go deeper into those corners. So it takes even longer for them to reach the detector. So if you have a really good kind of release mechanism, which we would call a pulsar, something that holds those ions and pulses them out, and a really good timer at your detector that's very specific, we can get very, very specific data on the mass of each of these fish or each of these ions in the case of a time of flight mass spectrometer. So the pros of time of flight, it's high resolution. That's great. We can really, determine small differences in mass. It's fast. And also heavy ions are detected pretty well in a mass spectrometer. Like you can run up to 20, 30, 40,000 M/Z and still see those, because it is, like I said, it's like a race and these big guys are slow. So as long as you're timing for long enough, they'll eventually hit the detector. So that's a good benefit. The cons for time of flight, one thing is they're kind of bulky. Modern time of flight instruments are much, much smaller than they used to be and now fit on a bench top. And really, we've kind of overcome that drawback, but you still have like a bulky chamber that you have to regulate the temperature and keep everything very stable. And these usually aren't as sensitive as a quadrupole. You lose a little bit, same as a trap, because you're having to hold the ions and then release them. So anytime you're spent holding ions is time where other potential ions are lost. So we refer to that as duty cycle, but that's probably the drawback. And I'd say in mass spec technology these days, we have a lot to gain in TOF sensitivity. So you'll continue to see more sensitive instruments in the future. And now they are as sensitive as a lot of triple quads. So this is kind of my preferred technique, by the way. So in typical time of flight mass spec, if we are just doing a full scan, what it would look like is our ions come through, they're held, they're not fragmented, they're held in a pulsar, and then they are shot through to the detector where you get a nice signal. Adding on to that is kind of like I talked about, you could have a quadrupole, but you could also have a triple quadrupole. You can have a time of flight, but you can also have a QTOF. So if you've heard people say QTOF, it doesn't stand for quantitative time of flight, which I think is what I thought when I first saw QTOF years ago. It actually stands for quadrupole time of flight, and it's a combined technique. So in a quadrupole time of flight, we're using that quadrupole to select an ion. In this case, the little blue fish gets selected through our quadrupole. And then we're using another quadrupole to fragment that fish. And don't worry, the fish he was already dead. He died of natural causes. So when you see the cut up fish, it's okay. We didn't cut them up just for the purpose of this. No little blue fish were harmed in the making of this. So we've got the fragments of that little fish, and then it's the time of flight that we can then look through all those little fragments and get good, high quality, high resolution data on not just the parent compound, but all those fragments. So that's where time of flight can become very, very specific. So not only are we able to, with good accuracy, with good resolution, determine the mass of these fish or bits of fish, we can see all its little fragments. Okay. Oh, and then I have another little animation. So this is what it looks like, a little more in a less fishy setup and a little more QTOF-y mass spec-y setup. So we have Q1 selecting our 215. So one of these ions, that'd be the green ion, lucky green ion, goes through and then gets busted up into our fragments. And like in Quadrupole, in QTOF, you can control that fragmentation. You can optimize it to be ideal for a certain fragment and be more specific to get the perfect fragmentation for, let's say, 185, or you can set it to be more of an average of collision energy so that you get a a collection of fragments. And I talked through the animation. I'm going to do it one more time. So the ions enter the analyzer and make their way to the detector. Good. I don't want to just talk over the animations. They're there for a reason, right? Okay, so that's the end of part one. Then part one was kind of the introduction into different mass spectrometry techniques. Now in part two, I'm going to go more into the definition of specific terms. So again, bringing it back to basics, we're going to look at a mass spectrum and chromatogram. And that's pretty basic, but it's actually really important when we're thinking about looking at this data that we distinguish between those two, and we think about what we can do with each of that, each type of data, whether it's a mass spectrum or a chromatogram. They're both very related to each other. Also going to talk about mass accuracy and resolution. Probably would have been better if I defined those first, since I've said them a lot, and you may be thinking, what the heck is accuracy and resolution? But it'll all make sense in a minute. Mass to charge ratio, isotope ratio, tandem mass spectrometry, we've covered that a little, and then different types of workflows and target screenings and non-target. So just to get started, a mass spectrum is simply the plot and on the x-axis, so it's the plot of the mass, or here the mass to charge ratio, which I will cover, just hold your horses on that, but the mass to charge ratio, and then intensity. And so all of these analyses, we talk about mass spectrometry being quantitative or qualitative. Well, technically, every time you do mass spectrometry, every time you create a mass spectrum, it's somewhat quantitative. Kind of depends on how you got there and the degree of usefulness of this intensity, but you do have a mass versus intensity. Your instrument is saying at that moment in time, this much of this thing hit the detector. We call this a profile mass spectrum, and it's showing you the apex, but then it's also showing you that those ions didn't perfectly move through the detector. There was some dispersion, and you will see the correct mass and then a kind of a collection of that spread. And when I get to it, that spread is really resolution. So you may see mass spectra that look like this. You may see them that look like, and then just going back earlier to my history example, obviously this is a mass spectrum. You can tell this is a mass spectrum because we have mass on the x-axis and we have some type of intensity on the y-axis. The other way you can see mass spec data, we call this centroid. So instead of seeing that whole dispersion of ions as a peak in your mass spectrum, we create a single bar, and the single bar is on the apex of that peak. And in a lot of cases, this makes it much easier to look at mass spec data. You lose the ability to see kind of the degree of error on your instrument, but you will see mass spec data this way too. Sometimes for library searching and that sort of thing, this is the way you will see data. Mass to charge ratio is pretty important here. A lot of people will do mass spectrometry for years and never really consider mass to charge because they only deal with singly charged compounds, while other people, specifically people dealing with peptides and proteins, are constantly dealing with mass to charge ratio. The reason is if you do have a multiply charged compound, so more than just a single positive charge, maybe two positive charges or three positive charges over that structure, it will actually move more quickly through a time of flight, or it will move at the exact same conditions through a quadrupole as something that is at half of its mass if it's double charged, or 3 times its mass if it's triple charged. And just for a few examples here, so compound A, and this is a mass spectrum, so you can get used to seeing this. So compound A has an uncharged mass of 399 Daltons. And so this would be if you got out a calculator, added up the compounds in the formula or the elements in the formula, you would come up with 399. What happens in the front part of the mass spec, usually some kind of ionization, which is typically, gaining a proton. When you gain a proton, you also gain its little positive charge there. And we see in the mass spectrometer a M over Z of 400. So even though our compound weighs 399, we know that it gained 1 because that's that proton of the hydrogen, and we see it in the mass spectrometer as 400. It's very, very common. And I would say like in pharmaceuticals, in environmental contaminants, food contaminants, you'll mostly see that M plus H charge. There's plenty of other ones, and I think Carl gets into a lot of that in part 3 of this series. But what happens if we have compound B and its uncharged mass is 798 Daltons? So this guy just happens to be, and I kind of made these up to be examples, but if it was to gain 2 hydrogens, so let's say it was kind of a bulky molecule, and on 2 different parts of the molecule, it had like an amine group that could gain that proton, then its charge would be 2+, and just exactly the same as compound A, it would show a mass to charge ratio of exactly 400. So even though these are 2 compounds of greatly different mass, so 399 and 798, they would show up exactly the same in a mass spectrometer. And even, you can go up as far as you want with this example, a triply charged compound. So this guy at 1197 would take on 3 hydrogens. So its M over Z would also be 400. So simply using that, what we would call monoisotopic, that main peak, you wouldn't be able to tell apart these 3 compounds because that charge you must divide that mass by the charge. Hopefully that makes sense and doesn't confuse too much, but it is important to know that in a mass spec, we are not just measuring mass. We're not just measuring Daltons or AMUs. We are measuring the mass to charge ratio. The other ratio you will see a lot, this is the isotope ratio. So if you remember back to Chem 101, when you calculate a chemical formula, it's never just kind of like carbon 12 plus oxygen 18, so it's exactly, or it's 16, so it's exactly 28. There's always some kind of decimal points there. And the reason is because almost all of the compounds in the periodic table have these natural isotopes that exist in nature. So carbon, which we know is 12.0000 AMUs, 1.1% of a natural mix of carbon actually is composed of carbon-13. And that's a little tricky in a mass spec, which is measuring things based on mass. It doesn't give 1 peak for carbon. It would give 2 or possibly 3, but probably 2, because I think C13 is the only real natural stable isotope. But you, instead of seeing carbon as that average molecular mass, you see it each individual peak. So we call the first peak usually the monoisotopic peak, and then we have additional isotopes. And it gets even more complicated when you have a chemical formula, because if you have like 15 carbons, you have quite a bit of carbon-13. So you see a bigger and bigger peak of that carbon-13. The same with compounds like sulfur. Sulfur has a natural isotope at 34 that's 4.2% of the total isotopes. So when you add these together, you get not just a peak, but you get 2, 3, 4, 5, 6 dozens of peaks, which you would think like, oh man, that really just made mass spectrometry more complicated, but it actually gives you a useful tool here. And the useful tool is the ratio of your monoisotopic to your other peaks. So just as an example here, I used a compound torodeoxycholic acid. So this is a natural component of bile. So it's in the liver of especially kind of fish and birds. And I'll tell you in a minute why I use this one, but it has a formula with some sulfur, and you can see, and lots of carbon, and you can see it has a distinctive isotope ratio, 100% of the signal here at 498.2, and then 30% of that is 498.2 because it's negatively charged. So 499.2 and 501.2. But when we look at this and we want to look at a different compound that has a very similar mass, like PFAS. So this is perfluorosulfonic acid. If you've dealt with PFAS compounds at all, you've seen this one. It has different elements, and so it has a very different isotope composition. So if we back up, you would see that 100%, 30%, 10%, and then for PFAS, 100%, 10%, 6%. So different, not completely different, but that different ratio can be used to validate an identification. So if you do have a compound and you think it's PFAS, but this ratio is way off, you see like 50% of the second peak and 20% of the third peak, that's a red flag that says that might not be PFAS. And you may need to go a little deeper into your identification using fragmentation, that sort of thing. Another interesting thing that happens, we talked about M over Z and multiply charged. So here, just because isotopes typically differ by the number of neutrons, if I'm remembering all this right, it's typically differences of 1 because neutrons are 1 mass unit, right? So that's why we see a difference in the isotope ratio of 1. When you go to doubly charged, the difference in 1 is actually a difference of 0.5 because we have to divide everything by the charge, which is 2. So your isotope cluster is now separated by 0.5. And this is a good flag if you're looking at data to say, to tell you if something is doubly charged. We often look at that isotope ratio and we say, just by how far apart that cluster is, you can say if it's 0.5, that's a doubly charged compound. If it's 0.33, that's a triply charged compound. And if it's smushed together and your peaks are 0.1 apart, that would be like a +10. So that is isotope ratio, useful tool to confirm chemical structures and identifications, also a useful tool to determine the charge state. Okay, moving right along. So chromatogram, different from a mass spectrum. And this is good to know and good to think about. So instead of mass on the x-axis, we have time on the x-axis, and still intensity on the y-axis. And this is usually like kind of the bread and butter. You would see a total chromatogram. That's all your data summed together. You might see an extracted chromatogram. That's just one mass extracted or a range of masses extracted over time. The reason you plot it over time is usually when you have a technique such as liquid chromatography. This is separating your compounds out, and you're able to take multiple scans over the course of a run. And when you do want to do your quantitative analysis, you can integrate the area under that peak. And if you come from a quantitative background, you know exactly what I'm talking about. You can build a standard curve. You can compare fold change, all by integrating that peak. And I think the tricky part when you're thinking about all of this is that LC-MS data is 3-dimensional. So it is a chromatogram, which is time and intensity, but at each data point, we have a mass spectrum. Or if you look at a mass spectrum, you can take any of those masses and plot it over time. So there's always 2 layers to our data. There's not just its intensity over time, it's also what mass are you looking at what intensity. So that makes mass spec data very complex, and it means that your software needs to do a very good job of giving you the results you want, so that you don't have to kind of manually go through each peak in a chromatogram and look at every single mass that's in there. You need tools and kind of automation to pull out the data you want. Okay, so to resolution. So this is where our accurate mass really starts to shine. Resolution being the ability to separate ions of similar mass. And in this example, I have torodeoxycholic acid. So this is the bile acid I was talking about, and then PFAS. And the reason I put both of these in there, these are actually 2 compounds that when you use a triple quad cause you really big problems because they're at a similar mass. If you look, I know it's probably small, but you have a sulfate or sulfonate fragments on both of them. So they create similar fragments in triple quad analysis. And they have pretty similar chromatography. So to separate these 2 out can be a little tricky. It can make your run a little longer. And I use this example because we can show with high resolution what we can do that is maybe more tricky in triple quad. So with these 2 compounds, and sorry, going back real quick, their mass is 498.3 and 498.9. if you were to use a mass spec that had a resolution of, okay, so if you were to use a mass spec that had resolution with a peak width of about 1 m/z, your two compounds would separate like this. I left them as fish. I'm calling this my P fish, just as the example. But what you would see here is not good separation. This is a problem in our analysis, and it's not good enough to separate the two compounds. How we would calculate this resolution is by taking the mass, so we'll call that 498.3, divided by the peak width at 50%. So that's 498.3 over 1. Our resolution is 498. So that degree of resolution is not good enough for us to separate these two compounds. There's too much overlap. We would get some false identification. If we increase the resolution, so really by doubling the resolution, our peak widths are now 0.5. So we've narrowed those mass spectrum peaks. Doing our calculations, so mass divided by that peak width, our resolution is 1,000. You can see we're starting to separate these two compounds, but not completely. We're still getting some overlap. Your data still might be a little misleading with false positives. By increasing the resolution more, so this is a resolution of 5,000, you can see that we've actually separated the two compounds at baseline. So in this case, high resolution, 5,000 as our resolution score is all we needed to actually separate the two compounds. This is easily achievable by a QTOF or by ion traps. This is about as good as you could possibly get with the best, most tuned quadrupoles out there. So it's just kind of interesting to see in the context here how much resolution we need to separate these two compounds. Now, if we do go to a resolution of about 50,000, so this is more like a finely tuned QTOF can do this. You see these two compounds now, they're nowhere near each other on the mass spec, and we could actually fit probably 10 other co-eluting compounds with similar mass between them and not even be affecting our data. So it's just very interesting, that perspective. Once we turn up the resolution and really start resolving those peaks, it becomes very easy to separate out some of those co-eluting interferences that are a problem in normal triple quad analysis. Okay, so the next term is mass accuracy, and these two are just as important to one another. So resolution is how narrow those peaks are. Mass accuracy is really how confident we can be in our measured mass. You'll usually see high-res data to 4 decimal points, maybe to 5 decimal points. And to me, that's what I think about as accurate mass spectrometry. Once you say spectrometry a lot, it gets really hard to say. So there's a calculation here. It's a very important calculation when running high-res instruments. So mass accuracy, or mass error, is our measured mass minus our calculated mass divided by our calculated mass. So in this case, we created a mass spectrum in our instrument. We measured it at 498.83, but we know that PFAS should be at 498.93. So subtract those two, divide it by the calculated mass, and we get a very small number. That's good. It's hard to look at those very small numbers. It would be hard to talk all the time. 0.0002 is our mass accuracy. So we multiply it by 1,000,000. That's where the term parts per million comes in. If we made that a percent, we would call it percent. If we made it parts per thousand, right? But since we multiply it by 1,000,000 just to make the numbers easier to read, that's why accuracy is, you always see it in ppm. So in this case, minus 200 ppm. This is about the error of a good quadrupole that's kind of tuned up. This is about what you'd expect. And it's not great. That's showing a lot of decimal points that are kind of meaningless in that analysis. So we need more accuracy. So when we say high resolution mass spec, we're also talking about high accurate mass spec, which is why you always also hear it called accurate mass spectrometry. So in this example, measured mass 9382. compared to our calculator of 9302. So now we're down to a mass accuracy of 16 ppm. And then in kind of our relevant high res example, this is the data we would want to see. We're measuring a mass of 498.9300. The exact mass is 9302, and you can see the math. Usually what you expect from your instrument is to be plus or minus that 2 ppm, maybe 3 ppm, like in a matrix sample. In a clean standard, it'll always be better. But you can know that if you calculate a mass error and it's very low, it's near that 1 to 2 ppm range, you are very likely looking at the correct compound. It's possible that you're looking at a different compound, which is why we do fragmentation. So back to our example of our bile acid contaminant and PFAS. These two, to be able to separate them, you would need a mass error of 1,284 ppm. So I just said that QTOF can do 1 to 2 ppm, so piece of cake, no problem. So something that is an actual problem in triple quad becomes almost irrelevant in high res. And I just find that example very interesting of just the power that we sometimes take for granted when we do QTOF analysis. Okay, and then to add to that, just that extra degree of confidence always is going to come from fragmentation. So I showed this example earlier, just popping it up there again, just to remind you, when we're doing time of flight, we're not only seeing that parent mass, like I just showed, and that parent isotope ratio, we are seeing all the fragments of our compound because we're combining a quadrupole technique. And so in this case, PFAS are P-fish there, had the structure of PFAS. This is a real fragmentation mass spectrum of what it kind of looks like. And again, no fish were harmed in the making of this slide. But you can see that we're breaking that 498, which is the parent, into its little chunks. So 418, 329, 279, all the way down. And if you get some mass calculators out, you can calculate the formula of each of these and kind of piece it back together. I find that pretty fun. And it's a way that you can do pure non-target analysis. So you saw on that previous slide with the different fish, that fragmentation pattern is specific to PFAS, and it can be used to identify PFAS. So similar to our isotope ratio, we would have a ratio that we would see in our sample of the parent fragment to all, or from the parent to all its fragments. That should match, if we've created a library with a standard of that compound, should match to a pretty strong degree, especially if it was run in the exact same conditions, the library spectrum. So this fragmentation pattern, again, is something else we can do in high res that gives that extra degree of confidence when you're making an identification. Okay, already shown this. So workflows. In the scope of, so at first I talked about the different technologies, then I talked about the different terms. So now that we know kind of what we can do, how it's defined, I wanted to show a different, like kind of separate this in a different kind of workflows. So you can just think in your lab, what would you use these methods? What would you use these terms or these instruments for? In the environmental field, we like to break it down this way. And that's kind of breaking it down into 3 ways. So the targeted analysis first, that is really what we do with the triple quad all the time. It's what you maybe have done with GCMS if you've done quantitation. You have certain compounds that you're looking for in a sample, and you mostly want to know how much is in there. Suspect screening, you maybe have a list of compounds, but you don't really have standards for them. You want to test the library, and then non-target analysis. So in this PFAS series, we're going to go over all 3 of these and kind of define them. Today, I'm just kind of doing a general overview of each one. I'm going to skip a little bit here. So another set of terms and a set of technologies that becomes very important is how do we acquire all of this data, especially all this fragmentation data, in a short amount of time, so it doesn't take like a whole PhD's worth of work to collect one sample and to analyze one sample. And a main way we do that is with setting up our MS data acquisition. So you can do this in two ways. So you can do dependent analysis. So we call this DDA or IDA. So this is data dependent acquisition. And what we're doing here, we're using our computer, we're using our software to be smart to pick the biggest peaks in every single mass spectrum acquired in that instrument, and then fragment those in an additional scan. Whereas in data independent acquisition, we are always selecting kind of buckets of ions to submit to fragmentation. And I'll just talk briefly about each one of these. So if you set up a data dependent acquisition method, like I said before, you're using the data in your samples to determine what is next, like what is going to be the next spectrum taken. This looks like, in this example, we are going to set a threshold. So we have a mass spectrum, right? Mass to charge by intensity. And you can see in the spectrum, there's these 4 peaks that popped out. So what we want to do is in real time, the mass spec is going to take each of those peaks and do a full fragmentation analysis. So the data that we obtain is we get full scan data. So we know these compounds are present in the sample. Then we get, for this peak, a full fragmentation spectrum. For this peak, a full fragmentation spectrum, et cetera. So that is really going to improve the confidence in our analysis. We can do library searching and non-targeted analysis. And then the other way to do it, data independent acquisition. So in this case, we don't need the computer to decide what the top peaks are. In this case, we set predefined windows. So in this example, we have windows that are 20 m/z wide. So that quadrupole is going to set a 20 m/z window, let all those compounds in, and then fragment all of them at the same time. So we let in 20 m/z window, we fragment it, we get a spectrum. We let in the next, get a spectrum. And it does this very fast. So QTOF can do these in like 10 or 15 milliseconds. So we're able every single scan to collect all of this data for any potential compound that may exist in any of these windows. And this is awesome because for any peak that might not show above that threshold, any of those little guys, they're all going to be present in that final data. And for things like retrospective analysis, that's extremely important. There might be things in there you had no idea they were in there, and you can look at that data retrospectively. And then the last thing to leave here before I just go through a quick workflow example is just still to remember that this data is 3-dimensional. So when we're looking at this kind of complex swath data, at each data point, we're getting a mass spectrum and then possibly an MS spectrum for each of those peaks in that mass spectrum. So I say it's 3-dimensional. It's actually probably 4-dimensional since we're collecting 2 types of data. That's where this gets seemingly complex. It's where people's brains start to kind of wonder, like, how the heck do you use this data? But with your software set up correctly, with good libraries, with good techniques, you actually don't have to do a lot of this thinking. You don't have to think about it in this amount of depth because you'll have software that does it for you. It is good and always good to know, though, what's going on inside the box. So the last example, just to put this all to use, if we want to measure the concentration of PFAS in our water, just as a whole workflow here, and this is very common in the environmental field. So we'll collect our sample, our little fish bowl with our little pea fish. We'll use chromatography, which I didn't talk about a lot today, a whole different 101 series we could be done on chromatography. But really the point is we're separating compounds based on their properties. We're separating them from matrix, analyzing them in a mass spec. When we get to the mass spec, our PFAS is going to go through Q1. All that matrix and other crap is going to be ejected, and we will be left with PFAS, which will be fragmented into these little nice fragments and then put through the detector. What data we will get is we'll get an accurate mass spectrum. So actually we get a chromatogram. And remember, this chromatogram is actually multiple mass spectra plotted over time. So in this case, the scan time may be 0.1 seconds. We can see this data. So that's how far apart these points that we've smoothed together will be. We can integrate this to get a quantitative analysis. We can look at the ion ratio here to see if we match what we expect. We can look at the mass accuracy. It says 498.9310. We can look at how close that is to our calculated value. So that mass accuracy, that chromatography, that isotope ratio, those are all things we're going to use to say, is this really PFAS? And then we take it the next step. So then, since the mass spec is also collecting MSMS data, we look at that fingerprint. So before we only have mass, isotope ratio, retention time. With the fragmentation, we have a full fingerprint to compare to. That gives us nice confirmation. And then finally, since we did acquire full scan data, we can look through that sample and identify other knowns. So in this case, like 6,2-fluorotone or sulfate. And here's what a real data sample with a library match might look like. So maybe there's things in that sample that you didn't expect, but you screen them against the library and you found some unknowns. Okay, I sped up at the end a little there to hopefully leave plenty of time for questions here. We went over all the different terms today. We went over different techniques. That's a lot of information. That's usually pretty much the first half day or first day of on-site training that I try to introduce people to into these techniques with a little bit of hands-on. So hopefully that was useful. Again, be sure to check into the next webinar